out of object detection algorithms. So the main aim of the project is basically we have categorized the project into three parts. Firstly, we want to develop a real-time inspection system, which is to detect the hazardous substance to alert the security team. So I need to focus on the emphasize that it needs to be a real-time inspection system. There are many object detection algorithms which are very popular, but the thing with them is the scalability and the scalability issue. For example, there are many people who come up with object detection algorithm, but it is not usable in the real time. So our task is to make an object detection algorithm which is firstly which can work on real time, and secondly which is very reusable, as in it could extend to a wide variety of audience. So these are some of the instances of the sharp objects, like a possibility could be an axe, scissors, or a knife, or maybe a pistol, and this will alert the security team maybe at any mall or any airport security, like that. So that is what the use case of the project looks like. This is an image which has been generated by our model where various sort of detections are happening, as in these are real-time cameras which are captured, and you can see that the gun has been detected, and like the instruments which are hazardous, like they are being detected. So we have done a comparative study in this project. So on that note, I would like to comment that a comparative study is never a fair comparison, because whatever has worked for our model or our case study in this particular scenario may not hold true for all different scenarios. Also, for real-time applications, there are different choices which we need to make. For example, you need to compare on the basis of accuracy, or you need to compare on the basis of speed. So there are there could be different parameters or the criteria where you want to do your comparative study. For example, maybe your input image resolution could be one of the criteria. So why this is an important criteria is because many authors in the past papers, in many papers, have claimed that if the resolution of the input image is very low, then you won't be able to detect very small objects in the image. And if it's a high resolution image, then only you would be able to detect small objects. So in our case, we would need the object detection algorithm to work on very poor resolution also, because the object won't be very visible. Like if it's a footage captured from CCTV camera, we want our object detection model to basically scale well to that particular frames. So in that frame, the object would be very small in size. So in that case, input image resolution is one important factor. Then there could be data augmentation techniques. For example, how much you want to do horizontal flipping or vertical flipping, how much color gyrations you want to add. Then there is a training data set. Data set also plays a very important role when it comes to object detection algorithm, which I'll come in the next slides. And then there is this loss function, and what is your learning rate, and everything could be a parameter for comparison when you're doing a comparative study. So data set preparation. So basically we have divided our data set into six broad categories or classes, which are AK-47, axe, scissors, knife, sword, and pistol. So these are the six categories, six hazardous substances which we believe are mostly a user is prone to carrying or something like that. So these are the categories which we have divided. For each category, we have taken 100 plus images from different sources. These sources are Google images also, and our personal images also. Like we have captured whatever possible images of the objects which are there in a home. For example, scissors and knife are readily available. So we have captured them in keeping in different backgrounds and in different scenarios. After capturing all the images, all the data has been manually annotated using the label IMG tool, which the icon is shown here. So this manual annotation is also something a very challenging task when it comes to, because firstly you have to detect manually you have to locate an object and draw a bounding box around it, and that we did for 600 plus images, because every image had 100 every class had 100 plus images, and these annotations were captured in YOLO and XML format both. Why this is done is because,
Prasun, so sorry to
yes.
interrupt you, but you're telling me there is no such data set available?
So the thing, yeah, that's what. So, ma'am, actually, whatever data sets we found, they were only for the object detection. So what happens is there are certain algorithms so that if you give an image, it will be able to detect. But if it's a background image, like if the background is very hazy or you want to make it work on real time, so in that case, it would be a complete failure because you have given very nice images for training. So that is not what you will ideally expect in the real time scenario, because in real time there could be any sort of background in the
Yeah,
um,
yeah, I completely agree. So that
in
means
the
there is no real life these kind of images,
no, no,
all
no.
very high resolution and
Yeah, yeah.
very
So
good quality. That
yeah, yeah. We
mm,
researched for 2, 3 repositories, and all the images which were there, they were very good images. So we don't want all
mm.
the good images to be there. We want some good images and some bad images, like that. Bad
So
images in
now
the
that you
sense.
have worked so much on the data set, are there some data which has occlusion, uh, or is the weapon clearly visible in
Yeah,
all these?
yeah, yeah. That I'll show you in the demonstration towards the end,
Okay,
because you would be able to see that clearly for yourself. Because
okay.
what we did was, firstly, we did use some of the data sets which was available, but when we tried the model and when we tried scale, like when we tried it on the real time, we observed that it was not able to detect object because the background was very different. Like if there was a curtain of, if there was a chair or anything of that sort in the background, it will not detect. But if I give it a very good image, like with a white background and the weapon in the image, it is able to
Mm,
detect perfectly. So for that, we had to capture some of the real-time images, whatever possible. And for
okay.
that, we also used some of the frames from movie clips also. Like I had not mentioned it here, but there are certain movies where people use AK-47 and all these. So we took that frames as well. So
Mm,
that's also how we augmented our data. And also we captured it in both YOLO and XML format. So there is a Python script which can convert it to YOLO to XML and XML to YOLO. So we use that to our
mm.
advantage
So
because
there is a comment here by Shankar. So he suggests, can we add noise or embed the images on background in the available data set to simulate real life setting? So I think this is also
hmm,
doable. I mean, this is
hmm,
also an idea that can work, but the only thing is to actually do it.
yeah, yeah,
Adding noise is definitely something that you
yes,
can
yes.
do uniformly. But yeah, so if you want to embed this, maybe yeah, you can also do this with some batch processing,
Yes,
certain. Uh,
as you mentioned, so someone pointed out rightly in the comments. So we did what the person is trying to say is the data augmentation technique. So there are like
yeah.
adding jitters. So jitters is something which add some salt and pepper sort of noise to the to every image. So that we did, but we did not do it extensively because we wanted some real time images also. So we did a
Okay.
use data augmentation, but not extensively.
Okay. Yeah,
So
please go ahead.
yeah, so moving on, this is a sample of how the label me annotations look like. Here you can see there is a Pascal VOC, and then if you click on it, there is a YOLO format which is also available. And this is how label IMG looks like. Then there are, this is the brief description of the topics which are covered in the presentation today. So the motto of the presentation is that firstly, we will be seeing an implementation of the detector model, which is a PyTorch based model. Then there are some challenges which made us to move on to another model, which is faster RCNN. Then there were some other challenges because of which we moved to YOLO V3, and to scale it better, we moved to YOLO V4, and then to make it more real time, we moved on to YOLO V4 time. So there is a brief description of every model architecture which I'll cover, and each model is tested on unseen images and videos. Also, there is a live demo which is there towards the end of the PPT, which we'll come to. So moving on, firstly, the detector model. So this is a PyTorch based model. You may not have come across this terminology. What is detector? So this is the name given to the model. Like just like there is a YOLO model, there is a detector model, and it's based on fast RCNN architecture. So there are few points about it, as in it's a lightweight package, and all the architecture which is there, as in convolution layers and max pooling layer and the classification layer, they are embedded into one complete architecture. So it removes the requirement of storing the feature map and saves the disk space. So earlier we were doing all our training or collab and everything, so we needed some disk space because it was running out of memory and all. So for that we went ahead with detector, and it also uses a softmax layer. So these are the results from detector. As you can see, it is very good when it comes to mean average precision. So mean average precision is a criteria which is used when you are detecting objects in real time. So whenever it comes to the real time object detection, we always go with mean average precision. The better the mean average precision, the better it will be able to detect in the real time. Uh, I'm not talking about precision recall or any other figure. This is mean average precision. You can see the model weight here is 158.1 MB and FPS is very low. So FPS means frames per second. As you can see, it's less than one. So this model is actually not really scalable when it comes to real time, because the FPS is actually a very major issue. Uh, so I'll show you all these things. Like you can see, I trained this detector model, and you can see this model weight is 158.1 MB. And when it comes to detecting images, so it's able to detect well. For example, there is this image one which I tested it on. It is able to detect this image, but the wall time is 7.46 seconds. So the frames per second is very low. So we cannot use it for real time. And when we started the PPT, we remember that one of the main objectives here is to make it more scalable to real time. So as the FPS is very low, it is not scalable. So we went to a different model, which is faster RCNN. So there are, um, yeah. Hmm. So before faster RCNN, there were two other models which are based on faster RCNN, which were RCNN and fast RCNN. So after RCNN, fast RCNN came, and then after fast RCNN, faster RCNN came. So this is a YOLO based architecture only, which uses regional proposal network. So firstly, there is a convolution layer which extracts all the appropriate features from the image. And then there is a regional proposal network which detects whether there is an object or not, and then it predicts what is the classification of that box, like whether that box is a axe or whether that box is a scissor, pistol, what is the class or the category that object belongs to. The detection time is better than both RCNN and fast RCNN, and mean average precision is also better. And it uses SGD in the background as a backbone when it is doing training. So this is a peek into the architecture of RCNN. You can see that this is an input image. This is the convolution layer which extract features. And then once these features are extracted, it passes on to this regional proposal network, which detects all the object. And then once that detection has happened, these red boxes are formed. So these red boxes are called region of interest. Like this is something which model believes that there is some object here. Like these are the potential candidates which can form an object basically. So then these are passed on to another convolution network, which does this multi-class classification and gives you the classification result, as in what is the object which is being detected and classified. So when it comes to faster RCNN, you can see the results, like mean average precision improved considerably. Like earlier it was 80%, now we are getting 90%. The model weight has also reduced. It has reduced from 153 MB to 74 MB. So it is more scalable, but the FPS is still very low. You can see the FPS is 5, and that too on GPU. So to work any model on real time, we need GPU, we need FPS of at least 25, like 25 or more than 25 FPS are needed on CPU. So there is still the challenge of FPS, as in making it work in real time. So this is not something which can be used for real time, but accuracy wise, it is the leading model, as in it's the best model. Here map as in validation map. Yeah, correct, Shuli. So map, whatever figures we are stating, that is with respect to validation accuracy, not with the training not with the training perspective. All these results are with respect to validation data set. For that, I would also like to comment that we divided our data set into 80-20 ratio, and our testing data set had 145 images in total, and training data set had 450 images. And these 90% figure is on the testing data set, which is comprising of 145 images and all. And the model size is also very low, but it's not scalable in real time. So to counter this, there is this another model which is called YOLO. So YOLO stands for you only look once. So it does not mean that you only look once at an image, like as in you don't need a single image only. It's not a single shot detector. It's what it means is you look at an input image only once. So faster RCNN has this problem that you need to revisit the image again and again when you are doing this pooling and all. But in YOLO, there is only single pipeline which does everything for you. So YOLO is built on the top of darknet architecture, which is a feature extractor basically. And then on the top of this, 53 more layers are added for detection, which makes it total 106 layers. And it outputs basically 6 number, that is PC. PC stands for prediction confidence. So suppose you predict a particular box, what is the confidence of that prediction? Then there is BX and BY, which is the box X coordinate and the Y coordinate of the top left. Then there is box height and the box width. And then there is C, which stands for class. What is the class of the box which you have predicted? And it uses one by one detection kernels and binary cross entropy for word processing. So this is a YOLO v3 architecture. You see that this is an input image, and when you pass it on to the network, there are total 106 layers. These pink ones are the convolution layers, green are the max pooling layers, and these yellow ones are the flattening layers. So that is how the YOLO architecture is whole for 106 layers. And you can see the result when we trained it on our model. You see that here at only 3000 epochs, the model started overfitting because the accuracy started dropping, validation accuracy. So we terminated the training at 3200 epochs, but you can see the FPS has improved considerably. Like earlier, which where we were getting only 5 FPS, here we are getting 36 FPS. As in it is more scalable in real time, but the precision and everything is still an issue, and also the model size. So for that, we built the YOLO V4 model, which Arpan will explain. So I'll request Arpan to take on from here.
Yeah. Okay, I'll share my screen. Okay. Yeah. So like YOLO V4 is like there's a one-stage object detector. Like so like usually like a one-stage object detector consists of this like following parts, which is at first we have the input layer, and then we have the backbone, which is responsible for feature extraction. Then we have the neck, which is responsible for feature augmentation, and then we do the like detection like in the head. So so like when it comes to backbone, there are like various choices available, like which are like pre-trained on like pre-trained on like image classification data sets like ImageNet, and then fine-tuned on the detection data set. For example, we have like CSP ResNext 50, and then we also have the CSP darknet 53, and also the EfficientNet B3. Yeah, but the authors of but the authors of YOLO V4 chose the CSP darknet 53 based on their theoretical justifications, and also they performed several experiments and found that like this is the like and they found that like this is giving the best accuracy. And for the neck, like so basically what the neck does is they are basically used to like extract different feature maps of different stages of the backbone. There is a lot of noise in the background. Can
Let me just mute everybody else.
Okay. Yeah. So for the neck, the choices were firstly we have this that FPN, which is the feature pyramid network, and also PAN, which is the path aggregation network, and so on. Uh, and for like YOLO V4, we are using spatial pyramid pooling on the CSP darknet 53. So what it does is basically it separates out the most significant context features, and at the same time there is like no reduction in like network operation speed, and and we're also using path aggregation network so parameter aggregation from so what it does is basically parameter aggregation from different backbone levels for like different detector levels, and we are using this path aggregation network uh, instead of feature pyramid network, which is like used by YOLO V3. And and we're actually not exactly using the original WAN network. We are using a slightly modified version of it, which basically replaces the addition with concatenation, like over there. But anyways, so the next is the head, which is responsible for detection, which like consists of both localization and classification. Uh, and for the head, they're using the same as that of like YOLO V3 only. And they have also made like several optimizations to like uh, increase the model accuracy without any extra cost and uh, inference. So yeah, so we actually faced some like issues while training like YOLO V3, especially that like yeah. So the main issue that we faced was that the training was taking a lot of time, and we were using Azure virtual machine for training, but we had like limited credits over there, and for 3000 epochs it was giving an ETA of over 7 days. So like we so because of that we like weren't able to show the results of like YOLO V4. But what we did instead was like we trained like YOLO V4 Tiny. So so like YOLO V4 Tiny is basically a compressed version of YOLO V4 with uh, dramatically reduced network size, and it also um, and it is also much faster in terms of both like training and detection. But it is less accurate. Uh, so for the YOLO V4 Shiny model, it took around 10 hours to train our dataset for 5,500 epochs, and yeah, and like just basically how the training happened, and
So
yeah, so
Shivli is asking what is your batch size?
the batch size is 64. Yeah. Okay. Yeah. So yeah. So basically, for the YOLO V4 shiny model, the I mean, like as you can see, the prediction is really fast over here. Like we are getting around like 160 like FPS on GPU, and at the same time we are also getting some like reasonably good FPS on CPU as well. So it is like really scalable on like various types of devices, and also the model weight is also like very low. Yeah. So like moving on,
But the
I'll just
MAP is not so good, right?
yeah, the MAP is like lower than like detector
Hmm.
or like faster RCNN. Yeah.
So you
So
have to trade between speed and this.
yeah. So now I basically have a short demo. So yeah. So so basically like we have like written a code. What I mean like what it does is basically like just let me clear my screen. Yeah. So what it does is basically like takes the video input from the webcam, and then like runs our model on it. So I'll just start the uh, okay, it showed up. Okay. So like I have a few sharp objects with me that I'll for example, I have this scissors. It is able to like so like it is able to like detect it like even if I take it like very far away, and yeah, and it is also like able to detect it when I like put it in front of my face and stuff. I also have this uh, I also have this knife which is able to detect. There are slight problems with it, I think. Uh, okay. And I also have this toy pistol. Yeah, it is
So it's
like
not possible to read the accuracy or the confidence with which this is being predicted. I think the color for the bounding boxes, or you can make it slightly bigger.
it is showing the confidence uh, uh, like on top actually. It
Yeah,
is
yeah. Just difficult to read because of
yeah.
the like I cannot make out the
I'll
number.
just do one thing. I'll just show you this. Like for example, not, yeah, here like we have like so basically it gives like a confidence score like in this way. Okay. Yeah. So like there's just an like image that I tested it on, and so yeah, and for this to work on like the uh, webcam like we did here, like we also had to like
Your confidence
convert.
scores are scaled 1 to 10 or something. What is the
Yeah, 0 to 1. Yeah,
0 and 1?
yeah,
Oh, between 0 and 1. I see. Okay, okay.
yeah,
So 1 is good. Ah, okay, fine.
yeah. So yeah, and also yeah, and also for this to work on the like webcam like we are using in the Python script, we actually had to convert this this like YOLO v4 darknet model to like TensorFlow format. And like what we were like also trying to do was like we were also trying to convert it to like TF Lite format, but we were like not able to like do it because of like TensorFlow versions. So basically what TF Lite is basically for like porting this model over to like mobile devices, like like and stuff. So yeah, so that can be like one future scope of this project. Like yeah. So I think yeah. So now like that was the live demo that I have, and like now I like gave it over to Prasun to conclude uh, the presentation.
Thanks. So, ma'am, we saw that, and everyone, we saw a light dam.
Prasun, your voice is not clear. It's from far away.
Is it okay now?
No.
Yeah, so we just saw a live demonstration.
Cannot hear you.
Hello.
So it was better earlier. I don't know. Now your voice doesn't appear clear.
Is it better now?
Can somebody else give a feedback?
Try to come closer to your mic.
Hello. Better now?
No, not really. Did you change some setting?
So uh, like I will only like present the uh, conclusion then. So
Okay.
basically like what we have seen so far
Arpan,
is
is
that
it better now, my voice?
Yes. Yes. Yes.
Yeah, it is better. Like you can
I'm
present.
sorry, there was a network issue. So I'll quickly wrap it up in interest of time. So, ma'am, we just saw a live demonstration and we saw that it was able to detect in real time, keeping in mind the different backgrounds also. Like when you keep it in front of your face or somewhere else, it was able to give a good detection with good accuracy score. So though you were not able to read it correct like at that time, but it was fluctuating very much. But the confidence score was between 60 to 80% like that, not even the perfect confidence and not very low confidence for all the objects which Arpan showed. Then there is a very quick summarization of all the things which we have done. So as we just spoke about the real time means greater than 25 FPS. So we saw that detector and faster RCNN does not have a very good FPS, but they do have a good map score. And the size is also one of the very big issue because they are 158 MB or something of that size. So that is something which is not which we don't want. So this YOLO Tiny V4 is better because it's more it has better real-time inference. Then it has a better MAP score, which is 74%. The size is also very less, that is 22 MB. So we can it's more usable across the mobile app and Android app like that. So since YOLO V4 Tiny satisfied all the criterias which we had planned to compare our model basis on. So we rightly went with YOLO V4 and integrated it to the live demonstration. We then the final conclusions and finding are like that. So even though faster RCNN and detector, as we just saw, are more accurate for object detection with accuracy of 80 to 90%, and YOLO V4 Tiny is not as much accurate with mean average precision of only 77%, but actually it's much faster and it can be used on live video, which is one of the main aim of the project. Then there is also one of the aim of the project was to make it more scalable. So when it comes to the model size, YOLO V4 Tiny is more scalable to mobile and tablets, and other object detection algorithms or models are not. So this was the final conclusion, and here are some of the future scopes of the project. For example, at this moment, we had trained our model only on the 6 classes, but there is still a potential to add more classes. there was also one thing called TensorFlow light model. So light models are something which are very, very lightweight, and even their size do not exceed more than 10 MB. So that is more scalable for Android apps and all, and that is widely used. Even that is, up till now, whatever implementations have been done in Android app for Python scripts and object detection, that are done using TensorFlow Lite. So we did try this TensorFlow Lite model. We tried different versions as in MobileNet and ResNet and all, but we were not able to integrate it to the Android app because there were several Java issues and all, which we were not able to figure out during the limited time which we have. So that's why the Android version APK we don't have as of now, but we can make one as a future scope of the project and definitely try to include it in our project report. And accuracy figures. So as we just saw that the mean average precision is 77%. So there's still scope for improving it if we have more Azure credits, or if we have more more powerful VMs, that is virtual machines in that sense. Because whatever training and whatever accuracy figures we quoted here, we did not use Colab for that. Colab was always crashing and having memory issues. So everything we had to run on VPM, but provided that we will have better VMs in future, we can get more better accuracy figures, and more accuracy figures mean more efficient model, obviously, that can give more FPS, that is frames per second. So these are some of the references of the paper which we have referred to, that faster RCNN paper and comparison papers, and YOLO V3 and V4 papers. And that was about our presentation. So we would like to stop here and would like to answer any questions if there are any.
Is your network down again, Prasun?
Yeah, I said that that was about our presentation, and we would like to answer any questions if there are any.
Prasun?
Hello?
Yes, Prasun. Hello?
Yeah. Yes.
Sorry, it looks like my network was down. Hello?
Yes, ma'am.
Yeah. So actually, yeah, interesting presentation. So what I would like to ask actually are two things. This is what the problem that I'm looking out for. So what about how much of occlusion is acceptable? Second, what about projective transformation? So your model might perform well even if the object is rotated, let's say scaled. That's what he showed in the live demo. So scaling is fine, rotation is fine. But what about projective transformation? So suppose, it's the object is on a table which is at some slight distance. So these kind of things, and the other is some level of occlusion. What level of occlusion is acceptable? These are the two things that I am interested in.
Yes, ma'am. So I would like to answer the second one first. Like, as you said, what if the object is very small? Like if it's at a far off distance, right? So
not just small, but also at not rotated or translated or just something like that. But there's actually a projective transformation. So you're watching at a distance, right? So that's a perspective. Yeah.
Ma'am, in that case, like my take on that is, like, if we increase our data set with such images and we train on that, so that can definitely scale well in that case. And also there is a challenge for image resolution. So as I spoke in the beginning, if the image resolution is not very good, like if it's a poor quality image, so in YOLO V4 model, what happens is if the image is of very poor resolution, or if it's not very good, even then it is able to detect very small object. But that is not the case with faster RCNN. So in faster RCNN, if the image is of poor quality, then you won't be able to detect very small images. And also that also varies from model to model.
So actually, you did speak about this resolution earlier. So what is the resolution of these images on an average?
Yeah, so
they different resolutions, or
they were of different resolutions, and we faced a lot of challenges around it. So you can see that input image resolution here is 416 by 416 for YOLO. So YOLO automatically scales all images to this, but when it comes to the detector model case, it is not able to scale well to all images. Like when because I told you we had captured images from all sort of resources, like personal images also and Google images also, and they were of different dimensions and resolution. So this detector model was failing considerably when we trained it on that particular sort of data set. So what we did was we actually
So
scaled
in
all the
terms of DPI, what is this? Do you know?
Hmm,
What
I
was the
mean,
resolution in terms of DPI?
um,
We'll have to check the DPI.
Yeah,
Because,
so that, yeah, maybe you can put it in your report. I would like to know
okay,
what was
yeah,
the DPI of some, like how
yes,
yeah,
low
we'll put it in the report.
you could go.
and
Uh,
actually we had to scale
and
every
did you
image
have
to
mixed
800 by
DPI
to make
images?
this one. Oh, sorry, ma'am.
Can you repeat the question, ma'am? Hello?
Yeah, so I think either my internet is not good or Prasun's. Hello?
Yes, ma'am. Can you repeat your question, please?
No, so I was saying that if you put in the information about DPIs of some images, that will be
Hmm.
useful.
Yeah, yeah.
Also, in the testing also. So if you test on some mixed DPI sort of images, low DPI, higher DPI, uh, so then that will be interesting to see. And then the other question was about occlusion. How much occlusion is acceptable to the model? Hello?
Like, I mean, we have, I mean, like, what we have tried to do is like we have tried to provide like highly occluded like images as well in our training set, but we have but like we haven't like tested it on very like highly occluded uh, like uh, like like images yet, but like we can
Yeah, it
like we
will be
can
nice if you can test on some of. So
yeah,
suppose
yeah,
there's just the barrel of the gun is visible, or the
yeah,
blade of a knife is visible, not the
yeah,
handle.
we will
Vice versa might be difficult, I understand, but if the blades are visible,
okay, yeah, yeah, we will
things like that.
test on this and we'll like add this to the report then.
Yeah, yeah. So how much sort of I'm not asking you to put a number on it, but just examples of what kind of occlusion it's working on, what kind of occlusion it's not working on.
Okay, yeah.
Yes, ma'am.
Okay, yeah. So those are all the questions and comments I had. If anybody else wants to ask or add anything, please go ahead. Okay, and doesn't seem like anybody has anything to add. All right. So then,
I have a
yes,
question, ma'am. Hello.
yeah, surely.
Yeah, actually,
Surely you're
my
not very
question.
audible.
Yes, am I audible now?
Uh, I mean, maybe Prasun or Arpan should, because my internet also seems shaky.
Prasun and Arpan, can you hear me?
Yeah, Shuli, your voice is very feeble. I don't know why.
Okay. Okay, then I'll ask my question later on. No issues. Yeah.
Hmm.
So you can put it in the chat if it's not too long. Okay, so let's give her a moment to type it up.
Okay, yeah. let's. I'm gonna just like Prasun, can you stop sharing screen? I'll just like try this out again. So right now when it is very close, the confidence is around fluctuating somewhere around 0.6 to 0.7 around that, and when I'm taking it far away, yeah, like when I'm taking it far away, the object is the confidence is actually like increasing because it is able to easily be able to I mean m- make out the like edges and all, I think.
So now can you actually put it behind your head or behind partly behind curtain or something like that? Not entirely, but yeah, slowly so
Okay.
that we can see what's the.
Yeah, yeah, it's in front of my face. It is yeah, the yeah, like when it is entirely in front of my face, it is not able to like detect it, but when it is slightly in front of my face, then the confidence is around like 0.3 to 0.4 around that.
But my question is that whenever the object is near to the camera, then confidence should be more higher than when it is like far away from the screen.
Yeah, actually it is higher. See, when I'm bringing it in front of, see, like if I move away and it is only like a white screen in the background, or like whatever it is. I mean, like
Okay.
if the background is like monotonous and I'm like
Mhm.
bringing the like object in front of the camera, then the confidence uh, like like is like obviously like very high.
Okay.
Yeah. But the thing that is happening is like when I'm like bringing it in front, uh, like I'm also like coming in the background, which is actually like decreasing the confidence a bit. But when I'm taking it
Mhm.
far away, uh, it is just like a monotonous background, so that is why the
Yeah, so it is not about being in near the camera or farther away. I think it's just about the background. That's what you're saying, right?
yeah.
Okay.
And that's because the edges are cannot be detected when it is on a almost same color background or not
Yeah,
a plain
exactly.
background.
Yeah.
Yes, ma'am. So ma'am, this background also like plays a very important role, I think.
Yes, so this is because essentially whichever model you use, essentially they will try to the weights will be I mean the model will try to segment right at some point. So that is what it is trying to do. Learn the edges, learn the segmentation, although it's not explicit. So if you occlude the background, like, or if you occlude the object, or you have a similar color background, then there will be difference. Okay, so anybody else has anything to add? Okay, so if nobody has any other questions, then maybe we can take a break for 10 minutes and come back for the next talk at 9 o'clock. I'll
Uh,
keep this link
and
open.
also, ma'am,
Yes.
can you give some like feedback on our project?
Yeah, sure. Please go ahead.
Hello?
Yes,
Like,
yes, please go ahead, Arpan.
so basically, I asked you for like if you can give some feedback on our project.
Oh, right now you mean?
Yeah.
So on the project or your presentation or what?
Uh, both actually.
Yeah, I think the presentation was good. The problem was definitely interesting. And as I said, I would like to see, since you have already, it definitely looks like you put in a lot of effort creating this data set. So one thing is, it will be nice if you put it up on your GitHub or something, this data set. And yeah, so there are those two questions that I definitely look forward to seeing how it works under perspective, and maybe not far away, but just some perspective, and under some partial occlusion. So these are two things that, yeah, but otherwise your presentation was very well. The explanation was quite good. I thought it was pretty clear what's going on. Although I would have really liked to see some precision versus recall graph. The MAP, I think, sort of, doesn't show that level of information. So yeah, that's what I would have. It will be nice if you can put in your report some precision recall graph or the rubric or something like that.
So actually,
Yeah.
we did have some precision and recall figures in our hand, but we did not include it in our presentation because we did not have it for all the models. So for the
Sorry,
fair,
I couldn't hear you, Prasun. You did not include
because we did not have it for all the models, like for detector,
okay.
did not calculate the precision and recall. So to keep a fair basis of comparison, we chose a criteria which was similar across all the models.
Okay.
But if you would like to know, so YOLO V3 precision is very less as compared to YOLO V4. YOLO V3 figure was giving only 63% precision like that, and YOLO V4 was giving around 77% precision. That's what I remember exactly at the end of the training.
Okay. Yeah, so I would say it was a nice. It is good to know. Uh, it will be another. I mean, if you want to continue doing this, since you have already done this yellow tiny, it will be a good exercise for you, or maybe you can even. Just because you have done so much work, the way to take it forward will be to try it on Raspberry Pi. Okay,
Yeah.
because it is a huge thing these days to make models work on handheld devices. So if you can make it work on Raspberry Pi, that will be something quite nice. Since I mean, if you want to do it, that will be something interesting.
Yes, sure, ma'am.
Yeah.
Sure, ma'am.
Since you have
Thank you
taken
so
this
much
much
for
effort
your.
already. Yeah. Yes.
Thanks, ma'am, and thanks all.
Okay, so then shall we come back after 5 minutes? Prasun here or left?
Yes, ma'am. Hello.
Hello.
Hello, ma'am.
Yeah, yeah, Prasun. So it struck me, but anyway, we can talk about it later. I don't want to steal time from the next group's presentation.
Okay, ma'am.
Yeah. So, all right. Are the presenters for the next topic here?
Yes, ma'am. Yeah.
Yeah, you can start sharing your screen. So Amey, Argadeep and Shankar are going to talk about emotion recognition